I have quite an interesting talk to give about flame graphs of visualization. And let's get started. So this is an interactive visualization for stack traces. My previous visualizations have included latency heat maps. And I've put an example here that's actually quite famous. Over 900,000 people have seen this heat map. It's actually one of my most boring heat maps. But over 900,000 people have seen it. Does anyone recognize this? No one. Oh, wow. I've got a few people who do. The 2 points where we have a higher amount of latency is where there's some guy in the data center screaming at the disks. So this is the latency heat map from when I was shouting at JBods. That was 5 years ago, and that went viral. And on YouTube, that's now had over 900,000 views. And I was actually giving a demonstration of latency heat maps. Although a lot of people, from the lesson they took from this is that you shouldn't shout at your disks in the data center because they don't like it. The newer visualization I've done is flame graphs. Unfortunately, I haven't come up with a viral video to really promote or sell flame graphs. Although I do get contacted by marketing a lot. Once you make one viral video that's had about 1 million views, then everyone in marketing wants to know you to find out if you can repeat it. Viral videos are not something you can repeat. It's quite a lot of luck. So anyway, that was heat maps. That's something I've done before. I worked with Brian Cantrell, and we put that into a product many, many years ago. And that was done for the first time. Quotes from yesterday at LISA: heat maps are a wonderful thing, use them, from Kasky Dixon. That's fantastic. And Theo talked about them as well. I did heat maps and visualizations in my LISA10 talk. At LISA12, I talked about performance analysis methodologies. And now I'm going to be talking about both at the same time, because with flame graphs, we get to explore methodologies that were normally too prohibitive, because there's too much data to sift through. So that is why flame graphs actually have a very big audience. This is for developers, sysadmins, support staff, performance engineers, for beginners through to experts. And it helps you analyze all software, kernel and internals. I'm Brendan. I'm the winner of the LISA Award for delivering IT in 60 minutes, or it's free, which I'll be proudly hanging up on the office wall. I'm also the recipient of the LISA 2013 Award for Outstanding Achievement in System Administration, which is awesome. I'm very proud, so thank you. I'm also the author of a new book on systems performance, which keeps getting sold out on Amazon when they order copies, but I had a look this morning and it was available, so hopefully they'll last a bit longer. I'm also the lead performance engineer at Joyent. We're a high-performance cloud infrastructure provider. At yesterday's keynote, Jason Hoffman talked about some of the design of Joyent and how we take systems seriously, we're doing innovation. And there's the wall of the Joyent office, and you can see on the right there's a number of flame graphs. So I think there's more. I need to take a more recent photo. We're also the core developers of SmartOS and node.js. This talk, it's really 2 talks in one. The first is on CPU flame graphs, which are really popular, and I'll explain how they work. And the second is on advanced flame graphs. So memory, I/O, off CPU, hot, cold, flame graphs, wake up, flame graphs, and a new one that I got working at about 4:30 a.m. this morning. And then developments that are happening in the world of flame graphs. Flame graphs, these will be interactive demos. I actually put them on GitHub about 30 minutes ago. So on github.com/BrendanGregg flame graphs. If you open them up in a browser, they're more interesting than they will be on the slides. And I'll be doing some of the demos in this keynote. So CPU flame graphs, the first part of this talk. It's great to start with an example of why we do these visualizations, what problem they're solving. I'll describe a real-world performance issue, and I'll just go through this quickly, and then we'll see how they work in detail. The problem was a production MySQL database that had poor performance. It was a heavy CPU consumer, and I used a CPU profiler to find out what's going on. There's lots of CPU profilers out there. Doesn't matter what operating system you're on, there's going to be one. The profiler that I happened to use, it was dtrace. It condensed its output by only printing unique stacks with their occurrence counts, sorted by count. when you're sampling what's on the CPUs at 100 hertz or 1,000 hertz, you can get a lot of data very quickly. And so by condensing it to only print the unique stacks, that reduced the data, so I have a chance of understanding what CPU code paths are hot. That's the profiler command. That's the last two stacks that printed out. That's telling me that the very last stack, this is a mangled C++, that was sampled on CPU 5,530 times during the 60 seconds I was sampling at 997 hertz. Great. So I can look at those last two stacks, because I'm actually doing this on the text SSH login, and I can say, maybe I should attack that last one there. That one is the most frequent. And that looks like it's in do command, dispatch command, calculate sum of all status. It's actually part of a system status. It's part of how MySQL responds to a show status query. However, there were over 500,000 lines elided from that output. So that's why I had the triple dot there. The full output actually looks like this. And that's the most boring visualization I've done. It looks like just a gray square. This is really hard to do, but I was really curious. Like, what would it look like if I took all the over 500,000 lines of output and tried to get an image of it? So I figured out a way to get it into a browser and snapshotted it. The first stack is in the top left corner. The size of one stack is tiny, and the last stack is down there on the right. There are 27,000 unique stacks. And remember, this is after the profiler has tried to condense the output to make it meaningful to read. So this is not just dumping every sample that has happened on CPU. It's already tried to condense it down. The most frequent stack, as I mentioned with show status, it's hard to tell if that's actually the problem, because it only accounts for less than 2% of the samples. So I need to really understand a lot more of this so that I know at least what 50% of the time we're doing on CPU, not just 2%. This is, I mean, for me, this is not just a haha, I've got to I'm going to have a bad day reading through this. This is a real customer issue, and our company was serious about solving it. I had this for our system, and I also had this for our competitor system. So I needed to understand in detail these two giant gray squares and figure out why they differed so that we could fix performance and not lose a very important customer. So of course, it looks nice when I talk about creating these visualizations and how excellent they are, but at the time, these are often created under duress. I have a really serious problem I'm trying to solve, and at the time, it wasn't funny when I was looking at this. I was actually pretty annoyed. So I tried a bunch of Perl to visualize it in different ways and came up with flame graphs. What I haven't done is, again, I was creating these under duress. I haven't saved all of the failures that I've done, but one of these days I'll give a talk of failures of visualization. The one that really worked was flame graphs, and the same gray square that you saw earlier as a flame graph looks like this. And I'm just going to switch to my browser. This is, I know the font's going to be very small, but I'll zoom in on later slides. And all these slides will be on SlideShare. All the SVIGs that I'm demonstrating will be on GitHub. This flame graph, it is not just an image that shows all of the profile data at once. You can move the mouse and navigate it. And what I've done, it's going to be too small, but I'll read it out. When I mouse over things, here I've moused over MySQLD do select, it will print how many samples that frame appeared in and the percent it was present in the stacks. So this is great. I could now actually understand where the majority of CPU time was by moving the mouse around and navigating. And I can see all of the profile data at once. And in fact, the show status stack is over there, and that was really not what was causing MySQL to be busy. Where CPU was really consumed was elsewhere. And it was very quick for me to have a look at this in the flame graph and compare it between the competitor system. And actually, we solved the problem. So all data in one picture. It's interactive. using JavaScript in a browser, you can do mouse overs. Stack elements that are frequent can be seen, read, and compared visually, and the frame width is relative to sample count. So this led to a 40% win just by understanding it, and that was great. That's their origin. They've now been used a lot. So, and they've also been adopted by other companies in other products. What I'll do now is go through the background of how they work and what they're actually visualizing. So for some of you, this may be very basic. For some of you, this may be a recap of operating systems class. This is all great. As I said, during this keynote, I'll end up talking about visualizations and methodologies, and this is also some OS internals. So a stack frame, which is what we're visualizing, shows a location in code. And it depends on the profile you're using to output it. This example shows the module, function, and instruction offset. A stack trace, or a stack backtrace, shows a list of frames. The index is the stack depth. And so the current frame, which may be on CPU right now, is in this case, it's mutex try-lock adaptive. And then the parent is mutex lock impl, mutex lock, and so on. You can go all the way back to thread creation or some origin event. These get put together as full stacks. This is what we like to sample to figure out code path. You don't have to read it all. You just have to read key functions. And reading a stack trace top-down shows ancestry. So at the very top, that shows where you are now. And then reading down the stack, you can see your parent, your grandparent, basically how you got there. Or you can read it bottom up, and that shows the code path from the origin that led to where you are now. So either way is fine. What I tend to do is, as I'm reading these, I'm new to stack traces, I figure out what are key functions. And then my eyes are bouncing between the key functions to figure out. I've highlighted a few functions here. And things like join, MySQL select, MySQL execute command, dispatch command. And that's what I see to figure out what we're doing in MySQL. If this seems new to you, I'll get into that in a moment. Two types of stacks can be profiled: user level for applications in user mode, and kernel level for the kernel. During a system call, an application may have both stacks. And I've got a very, very simple diagram of the operating system stack. So I said you might be new to it. You don't need to be a programmer to understand stacks. Some function names are self-explanatory if the programmer actually writes something intuitive. Others require some source code browsing if available. It's not as bad as it sounds. MySQL has around 15,000 functions in 500,000 lines of code. But you don't need to read 500,000 lines of code, and you don't need to read 15,000 functions. You just need to read that many. That's 20 to understand that stack. And once you understand those 20, you'll find that many of the functions are repeated, they're key functions. And as you look at other stacks, there's not going to be that many unique functions depending on what you're profiling. So the entire body of software for an application may look really intimidating. It may be 500,000 lines of code. But the code that's actually active and is executing is a small fraction of that. You have a whole heap of code for initialization. You have a whole heap of code for doing backups or whatever disaster recovery or whatever status and monitoring, whatever all these features that just aren't turned on. So you don't need to let that intimidate you and discourage you from reading the source code. What you actually need is you need some guidance of, I get that it's 500,000 lines of code. What parts should I just browse to get my head around? And then I will be able to understand profiling. And the parts you should browse to get your head around, well, that's a flame graph. A flame graph is showing you what code out of that massive, massive code base is actually active. And so if you generate a CPU flame graph for your application or for the kernel, you can then use that as a hit list of what areas of the code it would be worthwhile to become familiar with. So, and you'll find it often cuts it down to, so in my example I said that's only 0.13% of the code that you may need to browse. Source code often has comments if the programs have been good. So again, you shouldn't be too intimidated about browsing source code. Even if you're not a programmer, that's fine. I've worked with a lot of people who have tried and they've found it's easier than it seems, especially when you have this flame graph technique of cutting it down just to a few areas to study. I mentioned if you have C++ signatures, you can use a demangler first so that things are much more human readable. In the presentation, I know I forgot to do this for some of the visualizations because my brain has been doing this for so long. I failed to notice that something's mangled. I can just read them. And so as I was going through the slides, it's like, I should run these through a demangler. Normal people don't do this. So I get that. So stack visualizations. We understand what a stack is. Stack frames can be visualized as rectangles. Function names can be truncated to fit. Color can be chosen randomly. I'll talk about what else we can do with colors. So a stack trace that I showed earlier, just a portion, turning that into a visualization, very, very simple. This is just a column of rectangles. I picked random colors to differentiate between frames. Now, if I sample them and then show those columns of rectangles, it kind of looks like this. Sampling, we tend to want to do as often as we can to get accurate data, but not too often that we hurt or injure the performance of the target. So I may be sampling at, say, 100 hertz or 99 hertz, so I'm not sampling in lockstep. If I try and plot these as a time series over say, the scale of seconds, your visualization looks like this. And that really doesn't work. That's one stack sample. When zoomed out, the stacks appear as narrow stripes. And what we can do to improve it is we can merge adjacent similar boxes. And so if I have two boxes that are adjacent, this is in my time series graph. If I have two boxes that are adjacent that are the same thing, then just merge the horizontal space so that we have more room to decorate it with a label. And so if I had those three columns, it could look like this. That's much better than just these narrow stripes. That sometimes works. If you had a repetitive single-threaded app, that often doesn't work. Because we have multi-threaded apps, code path is changing so frequently. And the previous slide, I was already doing merging, right? This actually is doing merging anyway, and I still can't make sense of it. But merging is actually a good technique. The problem is we're just not merging enough. And so what the essence of flame graphs is when I realized I don't need this to be ordered as a time series. I can use a different x-axis ordering to increase merging. Time series is great. It helps solve a class of problems, and you need it so that you can see how things change over time. But the particular customer issue I was first working on, I just needed to know what that big great gray square was doing. I didn't need to know how it was changing within the 60 seconds of sampling. I just needed to know the big picture. So with flame graphs, I threw out time series. And on the x-axis, I sorted by alphabet. What it does is the sort is applied to the frame from the bottom stack upwards. And what this does is it optimizes merging so that frames are more likely to be placed next to each other where they can get merged. We have more horizontal space so that we can decorate it with the labels that you can read. So the x-axis of flame graphs it's really the population of samples. The y-axis is the stack depth. The colors depends on what you do with them. You can do different interesting things. For most of them, I've just picked them to be random colors to differentiate between columns and particular frames. Just to define flame graphs, and I've got a definition here. Each box represents a function. The y-axis shows the stack depth. I just mentioned that. The top function is what led directly to the profiling event. Everything beneath it is ancestry. The box width is proportional to the total time the function was profiled directly. All threads are shown in the same flame graph for these ones. You can do separate per thread flame graphs if that's useful. And they can be interactive like what I've done with Sfigs and JavaScript. Profile data can be anything, not just CPU samples. You can do I/O memory. As a naming suggestion, event, units, and then flame graph. If you don't have event and units, then by default, it's going to be the CPU sample flame graphs that are very popular. But I'm using flame graphs for other areas as well, and so are other people. So I could do a file system latency flame graph. As I mentioned, colors can be used for another dimension. Yesterday, I added a new one, and I'll demo that in a bit. So hashed on the function name. And for distributed applications, what you can actually do is merge multiple profiles in one flame graph. So instead of profiling, so the MySQL one that I've got here, that's all the threads of MySQL, all crammed in at once, and it makes a lot of sense. Even though these threads are of different types, so MySQL runs background threads and maintenance threads, they aren't on CPU a lot. The ones that are on CPU a lot are the worker threads. And so by sampling them, they span the majority of these get merged the most, and I can see the detail of where I'm actually spending my time. So even though it's multiple threads, fine to cram it together at once. And the same goes for a distributed system. I may be running MySQL or node.js or whatever it is across 100 nodes, and then I'm able to do one flame graph that shows the CPU usage across all of those nodes. To explain how they work, so to really explain it, what I've done is I've come up with a simple CPU sample flame graph, and I've just drawn it manually in Keynote. I'll illustrate how these are read by posing various questions. First question, which function is on CPU the most? No, well, it depends. People said A. It depends what you mean by on CPU. I should put the word directly in there. I mean directly on CPU. What is the CPU, the processor running? Which instructions belongs to which function? And that's the top edge of the stack. A is present. A is in the ancestry the most. But the actual instructions that CPU is iterating over the most belonged to the F. From the entry to F to the ret of F. Those instructions run CPU the most. So, and to figure that out, you look at the top edge. So whatever is the largest amount of the top edge, that is the thing that's burning CPU cycles. Now, that may not be very interesting. You may look at the top edge, and the top edge is a copy function, where it's just moving memory around. Or it's a spin lock. It's like, OK, it's a spin lock. That's all right. That's not actually helpful. I can't. It's helpful a little bit, but I need to know who called the spin lock. And that's when you go down to the stack and find the origin. So top edge is who's on CPU or who's doing that profiling event directly. May be interesting, may not be interesting, it depends. The next question, let's say it was a spin lock. And it's like, OK, so I'm spinning the most. Why am I spinning the most? Why is F on CPU? That's when I can look down at the ancestry. Well, F's on CPU because F was called by E. E's on CPU because E was called by C, and so on. Great. So the bulk of the flame graph is actually showing you the ancestry of how you ended up at the code that's running. How does B compare to G? You can visually compare lengths. And this is really important. This makes flame graphs intuitive. It means you can look at it and directly say, oh, I get it. Most of my time is here in MySQL execute command. And then between create file sort and select, I can see that it's about 40% file sort and 60% select, just by looking at it. There are many other profiler visualizations. In Linux, there's perf. Perf has this great cursors mode where you can navigate through profile data. Hands up if you use perf profiling on Linux. OK, so I've got maybe 7 people. Perf has different modes. It can also collapse stacks in different ways. And it's great what they've done. They've really taken text-based output as far as they can for showing profile data. But you have to read it. You have to read the numbers. With flame graphs, I can visually look at the distance and then immediately get a feel of where time is spent. Since the flame graphs I do are interactive, I can mouse over elements. And so I can mouse over B, and it says B was present 90% of the time, G was present 10% of the time in the tooltip. Different question, why are we running F? So why did F get called in the first place? We know it's ancestry, but what about at a higher, I want a higher level answer of why did we end up in F? And look for branches. And you can see them in the flame graph. So you could describe why did we end up getting to F as A chose the B path, C chose the E path, and that's how we got to F. Those branches are a place in the code where I'm spending a lot of time in down one path or another path. And so this might seem pretty obvious, but of all the areas of the code base that you need to study, those areas are the most important. So for MySQL, you can imagine like you're completely new to MySQL, you've never looked at the source code before. By the way, source code is not so bad, I don't mind getting into it. You've never looked at the MySQL source code before and you're thinking, Brendan told me that it may not be so bad because I may only have to read 20 functions. But the main thing you can do is you can look for the branches and read them first. And that may only be 3. And so a key branch here is the dispatch command calls MySQL parse. OK, so I should find out why the dispatch command calls MySQL parse. Another branch is join calls create sort index or do select. Now you should go understand that branch. And very, very quickly, you'll understand the higher level question of what is it doing by looking at those branches. Great. Now for some more real examples. So I picked a few. This one, a customer alerting software periodically checks a log. However, it's taking too long. It's taking minutes. It included running grep on an 18 megabyte log file, which took around 10 minutes. Grepping an 18 megabyte log file for 10 minutes? And grep seemed to be on CPU for that entire time. That seems really nutty. It was a problem for the customer because they were running this from cron tab because they wanted to check for various keywords to alert on their log. And the problem was if you check this every 5 minutes, then the cron tabbed tasks are stepping on each other's toes because one's still running when you're firing off the next one. And so they very much wanted this to run in 5 seconds or 1 second, not 10 minutes. That's the flame graph. So navigating it, like pretty quickly, I could see that we're in this routine called check multibyte string. And looking up check multibyte string, there's a function on CPU which is UTF-8 MBR2WC. When I saw this, I was completely new to this. And so I'm kind of looking it up. And I was actually with the customer. And the customer's like, UTF-8? Is this a UTF-8 problem? And very quickly, we realized it was. Lang was set to n_us.utf8. The customer had actually, how this became apparent was they had upgraded their platform to a new version. And on the new version, their alerting software was now becoming a really bad problem. So grep was taking too long, it was stepping on each other's toes from cron tab, and they're saying, well, you screwed up something in the platform upgrade. And that was it. It was just lang was set to n_us UTF-8. Switching to lang equals C improved performance by 2000x. This is one of the, it was also fun because I happened to be doing this at the customer site in person, live while they were watching. And so it doesn't always, you don't always get to do it live and have the amazing win. So that was very special. I actually blogged about it and got some interesting comments. Some people are like, yes, it's no surprise we know about this problem. Certainly one of the biggest wins I've had when you're in the 2000x territory. Now, that was a simple example. I did spot this from the raw profile of text output before I did the flame graph. And it's because the raw profile of text output shows how many unique stacks there are. And there's just not that many unique stacks in this flame graph. And so flame graph is very nice, but we did spot this straight from the text output to begin with. But it gives you an idea of of what the flame graphs can solve. I can demonstrate all of these as separate sfigs, but to get through them quickly, I did put them in the presentation, and I've decorated them with the mouse so you can see them. Okay, so next example. A potential customer benchmarks disk I/O in a cloud instance. The performance is not as fast as hoped. The host has new hardware and software, and we're worried about new issues or pathologies with the disk drive type. And so this was escalated to me. I do performance analysis all the time. Find out what's wrong with our disks. I take a look and notice CPU time was pretty heavy in the kernel. I would normally assume that was I/O overheads and not profile it. So a customer, I'm benchmarking disk I/O. Oh, I have a fair bit of system time. It's like, okay, well, you're probably doing a lot of IOPS. Each IOP has a tax. You have to do syscalls into the kernel. You're doing some kernel code paths, getting in and out of the file system, grabbing locks. I get it. I'm not going to profile that. I can assume what that is. I want to go work on the actual disk issue. Because flame graphs make it so easy, I will just roll a flame graph, because I can do that in a couple of minutes, just in case there was a kernel system time issue. Now, previously, I just wouldn't do this, because profiling the kernel and understanding it takes 10 minutes, 20 minutes. It just takes longer. But because flame graphs means I can do it so quickly, I'm now using it in situations where I wouldn't have before. That's what it looked like. And so I'm reading through this flame graph. And one of the top functions was 24% of CPU time was in TSC read, timestamp counter read. So why are we spending so much time reading our timestamp counters? Then looking at the ancestry going down, I found that 62% of the time we're in a function called ZFS zone IO throttle. And the customer was running a benchmark on a new platform. They were very unhappy about performance. They said, you've messed something up, because the previous platforms were much faster. And by rolling the flame graph, I could see straight away, the new platform does disk throttles. The previous platform didn't. At Joyent, we implemented throttles so that in a multi-tenant environment, cloud computing, one tenant couldn't monopolize the disks and cause these latency outliers that hurt other people. And there was a talk yesterday that actually had a great slide, scatterplot, showing from Jeff Darcy, showing the effect of multi-tenants on I/O latency. And so this is a problem that we've worked on, and we implemented a way to throttle tenants so that they couldn't hurt each other. And the way it works is it goes into ZFS zone IO throttle. It then does some spinning to create a delay for those IOs, so that it backs off one tenant, so that other people get a chance to put I/O into the queue. And that involves getting into TSC read. But I'd just completely forgotten about it. And of course, the way this issue was presented to me was, Brendan, we've got a new platform. The disks might have a new pathology. Maybe there's some guy shouting at them in the data center. So I've done a lot of disk analysis, and I've seen all sorts of weird and wacky things with firmware and hardware. But roll a flame graph, CPU usage, forgot about that. Problem solved. Third example, and this one was actually from Friday last week. Application performance is about half that of a competitor. Everything is believed identical. Hardware, application, config, except for the OS and the kernel. And since our performance is half, the customer is saying, well, something's wrong with your platform. Your kernel, your operating system isn't so fast. The operating system they were testing on was SmartOS, which is based on the illumos kernel. The competitor platform they were testing on was Linux. And the application was busy in CPU. It was busy on CPU, but it was 100% in user mode. And this is really confusing. And I'm thinking, you're 100% in user mode, and you're blaming the kernel? Close to 100%. See, the kernel can certainly mess you up. The kernel has all sorts of amazing. People assume that the kernel is a solved problem. In Jason's keynote yesterday, he talked about we need to innovate more in the operating system. I do a lot of work in the kernel, and there's just crazy things the kernel can do to mess up performance. It's interesting when people think that there isn't, and just to explain that a little, when a customer tells me about their environment, I've just deployed this great business environment, we're doing online shopping, we have all this stuff set up. When I hear customers describing it, I think, wow, you've made all that stuff work. There must be no bugs. You guys are brilliant. When we describe the kernel to other people, they have the same sort of attitude. Wow, the kernel does all this stuff. They must have no bugs. You guys are brilliant. It sounds really complicated. Actually, the kernel, just like the environment you create, it has bugs. All software has bugs. And so, but in this case, the performance was not in the kernel. The performance was running user-land code. And so it was really hard for me to get my head around, how is the kernel messing this one up? Maybe it's messing it up, like, OK, so user-land code, maybe it's messing up because it's messed up the way it does memory locality, the way it groups DRAM and memory. It's running threads in such a poor way, even though you're in user time, that your CPU cache affinity is low and the cache miss rate is high. Things like that. I profiled it using flame graphs on both platforms to get my head around it. And of course, not just to see what was going on. Because at this point I was doing a comparison between two flame graphs, I've added a hash option so that the colors are the same. So you can roll multiple flame graphs and it'll color each function name the same based on the hash. And that's what it looked like. So on Linux, we had this. My eyes focused on this part of the flame graph. That was what it looked like on Linux. That's what it looked like on SmartOS. On SmartOS, there was an extra function, unzip docID. Now, the function label formats are different. You can see they look different in the flame graphs. That's just because the profilers have outputted in slightly different ways. But having an extra function, now remember, the customer told us the application is identical. I'm running the same application. I'm running the same application on your competitor as we're running it on you. And you are slower. Your kernel is messing it up somehow. And then when I look at the flame graph, it's like, what? No, you're running a different application. You're running a different function here. So I brought up the source code, had to look at the function. That's what it looked like. This was actually in Sphinx. Unzip docID, return unzip offset. And so this is where the penny dropped. When you see a function like that, you think compiler optimizations. Compilers love to eat these things for lunch. Compilers will take that function and say, what, you want me to like initialize a stack frame just so I can call one other function and return? Like, what do you want me to do, waste CPU cycles? Functions will throw that away and call directly into the child function. Compilers will throw that away, throw the parent function away, call directly into the child function and return, just to save CPU cycles. And that was it. We had a renewed interest in looking at the compiler differences between these platforms, which had so far had been assumed to be identical, and saw that on Linux it was compiled using -03, and on SmartOS it was not. So very, very, like, almost embarrassing to admit. It's like, oh, really? But it's actually a really, really hard problem to find out if you're running an application and you don't have compiler optimizations that someone else has. This is an amazingly difficult problem. Imagine I told you you're running an application and performance is great. Oh, guess what? Performance now sucks for your application. Sorry. So what? What are you talking about? Like, nothing's changed. The workload's the same. You don't realize. Some compiler author out there just wrote an optimization, and so now your competitors are compiling. That code is now not running as fast as it could. Now you're leaving 20% on the table because you're not using the latest version of GCC. But this is just, it just hurts my head. You're looking at an application, right? You're looking at an application, and it's performing as fast as you can imagine. And if you describe the performance, you say, there's nothing left on the table. It can't go any faster. It's just beautiful, the performance. It's just a well-oiled machine. And then somewhere, a compiler author creates a new thing that you don't have. Now you're leaving performance on the table because you don't have the option. But you didn't change anything. So how do you see that in the flame graph? So this is a problem I struggle with. Because if I'm trying to see a flame graph or any profiler and know that you don't have a compiler optimization, I'm looking I'm looking at state-of-the-art performance right now, and I'm trying to guess what might be invented next by the compiler authors. It is really, really hard. Anyway, that's why I do flame graphs and I do differentials, and I can see if things have changed. It gives me a big clue. So more examples I'll get into in a moment. Flame graphs actually get much more complicated, many, many levels. Briefly, how generation works. So I'll describe the original Perl version I wrote and put on GitHub, but there are other flame graph implementations as well that have different features and usage. There are only 3 steps: profile the event of interest, stack collapse, and flame graph. So as an example, this one just happens to use dtrace. Dtrace profile 997 Hertz, that's doing kernel stacks. That gives me this giant gray square of text that I can't possibly read. I then have just a simple Perl program that folds it into a standard format so that instead of multi-line stacks, it is single-line stacks and counts. And that's what flamegraph then reads. And flamegraph will spit out an SVG. Stackcollapse.pl and flamegraph.pl, open source, I put it on GitHub. They're only flamegraph is only a few hundred lines of Perl. It's fairly straightforward. You can use pipes to avoid the intermediate files. That's fine. I actually like creating intermediate files sometimes because I'll go and edit it because I want to focus on some code paths of interest. The profile data at a minimum is a series of stack traces. It may also include stack trace counts. And so the dtrace output, it will already do in-kernel aggregations and say, this unique stack trace appeared 5,000 times. This unique stack trace appeared 10,000 times. Great, because that cuts down the amount of data that the kernel is spitting to user land. Your profiler needs to print full, not truncated stacks for this to work. And you really want symbols. You don't want this to be a list of hexadecimal numbers. And that may be step 0. Get the profiler to work in the first place. Once you get the profiler to give you a meaningful output for your target, then you can feed it into flame graphs. There are lots of different profiler tools. So dtrace exists on many different operating systems. On Linux, I will use perf. Perf has different ways of profiling, not just CPU samples, but can do hardware events, software events, OS X instruments, Windows X perf. There should be a profiler on whatever system you're on. And whatever the profiler is, if it can generate stack traces, which they can, you can then convert it into the format and feed it into flame graphs. So flame graphs works on anything. That's just an example of dtrace, and I'm not going to go through in the details of how to use dtrace, but it's just a one-liner for profiling the kernel and profiling user level. And I hope these work on Linux one day when we finish the dtrace ports. They'll be fantastic to get dtrace fully ported to Linux. Perf, which is what I use right now on Linux, just to give you a sense of what it involves, just some commands: perf record, all CPUs, call stacks, 97 Hertz, and then I'm outputting it to a file, and then I feed it into stack collapse -perf because it understands the perf format, and that spits out the single line format that I need. That's what it looks like for system tap, if you want to use system tap. If possible, you really want to, as I said, have all the symbols in the stack trace, and dynamic languages and the language virtual machines can be a real problem. So here I've got a stack trace that came from node.js's runtime, v8. And previously, this series of hexadecimal numbers, that's it. But you can't make sense of that. dtrace has this thing called a ustack helper that was created by my colleague, Dave Pacheco. And what it can do is when it profiles node.js, it will produce stack traces that show not just the native functions, but also the application level functions. And so I can see, oh, I'm actually in exports.active at timers.js at this offset. That's really useful. Once you get to that point, then you have a stack trace that makes sense. And then you can turn it into a flame graph. What stack collapse does is I've already mentioned this, so that takes a multi-line stack and it emits a single line. So the stack trace, the frames are semicolon delimited, and then it has the count for how many times that stack trace existed. Stack traces are typically multi-line, and living in the Unix command line, we like things to be single line because it makes it much easier to grep sed awk our way to success. So it converts it into this single line format, and then that gets fed by flame graphs. It's actually handy to have stack traces as single lines because I can grep them. And sometimes I'll profile the kernel and say, actually, I'm just interested in ext4, fs_dir hash. I can grep that before I do the flame graph. Now the flame graph is just focused on that. Or I might grep -v CPU idle to cut that out. The final output, the desires is we want it to have full control of it. I want to have full control of output. There are different visualization things out there, and sometimes they can be a bit restrictive. I want high density detail. I want it to be easily viewable by colleagues, different platforms. And I do want it to be interactive, so that you can mouse over elements and see what happened. And so that's why I used Sfigs and JavaScript. Sfigs and JavaScript deliver all of them if you open them in a browser. If you don't, if you for example, print it out and stick it on the office wall like we've been doing at Joyent, you still get at least 3 of these. If you turn these into pings, you still have full control of what the output is and high density detail. The generation of flame graphs, like I said, this is a fairly straightforward Perl program and has options. I can customize the title, the widths, the sizes, the color template, and so on. And of course, you can hack away and modify it and come up with additional cool things. So that's just a quick rundown into how the flame graphs, how they work. Profile it, fold the stacks, run it through a flame graph. Now you have a Svig. You may think, this is great, I'm just going to do it differently. Some people have rewritten flame graphs from scratch, the software, and so that they can integrate into their monitoring system or their analysis system. So that's just an example way of how you can go from profiler to visualization. Types of flame graphs. So CPU flame graphs are really popular, and this is where we measure code paths that consume CPU. That helps us understand and optimize CPU usage, improving performance and scalability. I do this all the time. I need to debug why performance is worse than competitors. It's commonly performed by sampling CPU stack traces at a timed interval, like 100 hertz every 10 milliseconds. Can be used tools like I mentioned earlier. CPU sampling, if you're new to that, that's very simple. I have a timer interrupt. It wakes up every interval and then samples the stack that's happening. I've drawn this flow. So this is time series flow of what your software might be doing. Function A runs. It calls function B. Function B goes into a system call that happens to block. Maybe it's waiting on disk I/O or network I/O. And so as we're sampling this, we're not taking samples when it's off CPU. We're only taking samples when your application is on CPU running code. So that's why it's profiling the CPU usage. It's coarse because things can happen in between those samples, but it's often effective. The different way to do it is to actually do function tracing, where when A begins executing, I gather timestamps. When B begins executing, I gather timestamps, and so on. That's much more accurate because I can fetch nanosecond timestamps. But the overheads of this can be prohibitive because these functions can be called very frequent. And if I'm only adding a small number of cycles, that can slow things down. CPU profiling. So like I said, sampling, coarse but usually effective. The other good thing about sampling is that it is low overhead. So depending on the stack type and sample rate, this can often be negligible, just to do CPU sampling of your application or the kernel. Tracing, the overhead can vary quite a lot. So definitely hesitate to do tracing. Now, as an example outcome, could you do this right now? So I've copied this description. As an experiment to investigate the performance of the resulting TCP/IP implementation, I hid the server names. The CPU is saturated but has about 30% idle time. And then we break it up. The time in system processing data is 20% Ethernet, 10% IP packet processing, 30% TCP processing, and 25% checksumming. It's pretty cool. Hands up if you think you could do this analysis and write a report like this. So I've got, is that no one? No one thinks they could do this? I think I could do this, but I'd be using flame graphs because I can then navigate them and get those percentages out. This is a really nice report, but it's kind of hard work to do this. So I'm glad that I have modern tools like dtrace or perf. I have modern visualizations like flame graphs in order to answer this question effectively. Where did this come from? That came from Bill Joyent in 1981. So the mind boggles about how he was able to accomplish this so many years ago. That's an intimidating thing to do. And, but it's also very useful. So thankfully today, you can actually roll flame graphs to do this. But it's just one of my favorite quotes. This is the sort of thing we're doing with flame graphs, is that we're quickly able to break up our time and figure out where it's spent. So as another example of CPU profiling, a file system is archived using tar. The files and directories are cached, and the runtime is mostly on CPU and the kernel, Linux, where exactly? Just like Bill Joy was trying to figure out when he was developing the TCP/IP stack for BSD, where is the time spent? There's the flame graph. I've sampled the kernel. I can see by mousing over, 20% of time is in sys getDense for reading directories. 54% of time is doing file statistics. New fstat@. Done. Great. It's also good for learning kernel internals, because as you browse these stack traces, you figure out what code parts in the kernel are active, who's calling who, hierarchies, relationships, the forks, all the stuff I mentioned earlier. So flame graphs would actually be very suitable for operating systems class at university. So you can show students, this is actually what the kernel's doing. We know the kernel is 10 billion lines of code or whatever, but this is the stuff that's going on. And this is who calls who, and so on. You actually start to recognize common things in flame graphs. So once you start profiling a target, I start to recognize, yeah, that's the getDense that shows up from going into ext4. So here's some other example of common things that I tend to see. Just to give you an idea, this is the stack recognition. There'll be a test at the end of the keynote. So this is the illumos kernel. This is kernel CPU flame graph. And I can see there's my fused TCP receive path, my fused TCP send path. And great, I can see how the kernel's working and what code is calling who. This one was an issue we had in the kernel where there's a cache, the DCE cache, which caches routing entries. So who is routing to, so if you look up a route, the kernel doesn't have to parse the routing table. It has a very quick mapping. Anyway, it turns out there's a problem with the DCE cache, and it was showing up on CPU a lot. There's a flame graph that we were using to debug it, and you just look at these. We're looking for the plateaus, because that's showing the function that's on CPU executing, and then its ancestry. And it's like, why is this function just have all these plateaus where it's burning CPU cycles in the kernel? And very quickly, we start looking at it, and it's a kernel bug that was fixed. This is a KVM guest Linux kernel, and just showing you the code path of how it gets out of the Linux TCP send message. And of course, that's much too small to read, but I have a lot of them. So this is where I can browse it, and I can mouse over things and say, OK, so I get it. So when system call path, syswrite calls VFS write, we go into do sync write, and so on. And of course, as I'm moving the mouse around, I get to see the samples. These elements that are too small, I can still mouse over them and see what they were. So that's IPQXMIT for 0.97%. So all the data is there, I can figure it out. Syscall towers. This flame graph shows various towers that come from system calls. Syscall towers sounds like the name of a hotel. Actually, LISA next year will be held at Syscall Towers. Built in the 70s, it still looks a bit industrial, but they've decorated it. So if I mouse over all of these elements, I can see what they actually were. That was something that does show up a lot. It's going to be CPU syscalls, and so there's close, there's open, there's pulsys, read 32, stat 32, stat 64. And of course, I can mouse up here and figure out how that system call was actually working and the code path it was taking. So again, great for operating systems internal classes. Students can navigate it, figure it out, and learn the kernel quickly. this isn't about learning the kernel. I don't want to force everyone to learn the kernel. It's just about learning enough to do your job and to solve that issue, which is what flame graphs are great for, because it's only showing you what's active. So you don't have to go and read all that other stuff that isn't even on the table. You can do both stacks at the same time. So previous examples so far in this talk, I've shown either user stack backtraces or kernel stacks, flame graphs. And how you can do it is you can stack them, kernel on top of user. And as an example, this shows KVM QEMU. And I've separated the stack traces with a gray delimiter. But the top stack trace is the kernel stack, and the bottom one is the user stack. And so now when you're CPU profiling, you can see if I'm hot in user mode, my application, and if I go into the kernel and start doing a lot of work, I can see that that's hot too. So fantastic. That's CPU flame graphs. And that's like a talk all by itself. Now I'd like to do advanced flame graphs, which is what else you can do with this visualization type. So apart from CPU samples, stack traces can be collected for any event. So there might be I/O, disk, network, file system, different CPU events like cache misses, lock intention, memory allocation. And instead of counts, sample counts, you may be interested in latency, byte counts, or whatever. So as an example, memory. With memory flame graphs, we can analyze them to understand growth or memory leaks. And there's 4 approaches for doing this. Allocator functions, the break syscall, mmap, and page faults. This diagram explains them, and so this may be a recap of how this stuff works. My application has an allocator. It has various functions like malloc, free, realloc, calloc. It then consumes the heap. So, or however it's implemented, usually using a heap in virtual memory. And it uses the heap as a cache. So if I'm doing mallocs and frees, it doesn't need to keep extending virtual memory. It will keep a cache and then reuse memory. This is why it's often said that applications grow but never shrink. They grow in RSS but never shrink, because typically they don't have a means to shrink. Your process heaps just keeps growing. Depends on the allocator. The heap grows via the break system call. A different way to do memory allocation is through mmap and munmap. That's actually one way you can shrink, because you can munmap it. Our systems are all typically demand-based allocators. So when you malloc memory, you don't get a page mapping. You don't have a piece of physical memory in your process at the moment you run malloc. What happens is the operating system lies to you and says, sure, you've got that memory. But when you access it, that's when the lie falls apart. And what happens is a page fault, and the MMU, the memory management unit on the processor, then has to tell the operating system kernel, now is time to do that mapping. This is great because it defers the expense of doing mapping until you actually need it, until you go and write to memory. And that's when it does a page fault and maps it. Why am I going through this? All of these are targets for flame graphs. So you can do flame graphs for the allocator functions, breaks, mmaps, page faults. And they show that these are different views into memory allocation to help me understand what's going on. So for the memory allocator, I can trace all of them. They operate on virtual memory. I can create a memory allocation flame graph by just doing the alloc stacks and showing the bytes. If I also trace free and realloc, then I can do suspected memory leaks during tracing, so memory leak flame graphs, which is pretty cool. The downside is these are really frequent. So if you start tracing these, you might slow the target down a little bit, like 25%. If you're using a dynamic tracer like dtrace. That's not so bad comparatively. Things like Valgrind's memcheck, where it does CPU simulation, can slow a target down by 20 to 30x. So yes, these hurt, but it could actually be much worse. And you may do it for a short duration. So as a simple example, it's just a one-liner to go and say, trace malloc in my application, give me stack traces and byte counts, and then I can do a malloc flame graph. And I've moused over, in this picture, I've moused over an area, bash command word complete function. This is actually a malloc flame graph for the bash shell. And I can see that area, that code path, led to mallocing 20 kilobytes. And the area over to the left, where it's doing glob file name, that allocated, I could mouse over it and find out exactly, but just my eyeballs can say that's probably 15 kilobytes. So you can do this for, I picked bash because the stacks are short and it's a very nice simple example. But you can do this for any application and then quickly figure out, why is my application mallocing memory? What code paths lead to doing malloc? That's just one view of it. And that may not be as interesting as it sounds. Actually, it sounds amazing. It's like, wow, I've solved the memory allocation problem. I can just mouse over these things. I can roll this for your application, figure out why you're consuming memory. Well, as it turns out, malloc happens just because you're doing work. You can do mallocs and frees all the time. It's not a problem. That's what you do every time you service a request. What we're generally interested in performance is when we're not doing frees, or when we're not doing frees either because of a bug in the software that's a memory leak, or we're not doing frees because of a misconfigure and the application continues to grow. So this is interesting, but it's just one view of it. Yifan Zhang developed memory leak flame graphs using system-tap to trace allocator functions and applied them to leaks in Nginx. And this is fantastic. So he was able to produce a memory leak flame graph that showed you the paths that actually leaked memory by associating the malloc and free addresses. And there you can just show it to the developer and say, these paths leak memory. You can visually see which one's the worst, and then you can work up that stack and go and fix it. Fantastic stuff. When I saw him do this, I thought, oh, that's really cool, but surely the overheads would be a bit too prohibitive. And then I went and tested it myself and found it. It did slow the target down a little, like I said earlier, maybe 25%, but not as bad as some other techniques. It's not as accurate as some other techniques either. So Valgrine's memcheck is fantastic because it will find everything. This is only you can run this on a production if you can pay the tax and you can trust the dynamic tracing tool. You can run this in production for 10 minutes and then figure out what leaked or grew during that time. Break tracing, that's just a different way to look at the memory problem. And so on my diagram earlier, break tracing that's when the allocator can't satisfy the malloc within the cache that it's got, and so it needs to grow the heap. I like tracing break because these are infrequent. The allocator shouldn't do this that often, so we shouldn't be talking about 25% overhead. This might be close to 0. There's an example of doing a break flame graph, and what it's showing you is heap expansion. If you're running top and you see RSS is growing, and you're thinking, why is it growing? Who's doing this? This type of flame graph shows these are the code paths that led to growth, and the width shows how much they caused it. And so the width of these is actually showing megabytes, showing bytes. So fantastic. Anytime you're seeing RSS, now that I've been able to do this, anytime I see RSS growth in top, it's like I want one of these heap expansion flame graphs because it will immediately tell me why my process is growing and growing and growing. So great, has low overhead. The calls are typically infrequent. But it can, none of these 4 techniques are absolutely perfect. The reasons for break, it may actually be an innocent application code path that happened to spill over the current heap size, but there was some other code path that was actually leaking memory. So what I'm going through is 4 different ways to look at memory. No way is perfect, but they're simple, and each of them can solve different classes of problems. mmap can also be turned into a flame graph as well. This should also be low overhead depending on the frequency. If you're doing mmaps a lot, then you have another problem, and that is you're doing mmaps a lot. So in some operating systems, it depends on whether you're doing synchronous TLB shootdowns or not. In some operating systems, doing mmaps a lot actually hurts because we're doing CPU cross-calls, which would show up with CPU flame graphs. So if you run CPU flame graphs, you can actually tell that you've used mmap too much and you've been naughty. Page faults was the 4th type, and that is where the application actually writes to memory that was allocated, and it figures out the operating system had been lying to it all along. No, you don't actually have the pages of memory mapped. It's a page fault. That's when the MMU tells the kernel to go map it in. And that's great because this flame graph shows us, that's a page fault flame graph. This shows us who actually went to use, I need to pull that into my demos, who actually went to use memory. So the malloc flame graph shows the code path that happened at allocation, but you can imagine in your application you have one code path on allocation, but sometime later you actually consume it. That might be a different code path. That's when you actually write to the memory. And so you have the earlier malloc flame graph shows the allocation point, and then the later page fault flame graph shows us when we consume it. Two different ways to look at something similar. Like I said, they can solve different classes of problems. Great. That was memory. I/O. We can also do flame graphs for I/O. So we can show time spent in I/O like storage I/O. Measure I/O completion events with their stack and their latency. Merging to show total time waiting by code path. There's two types of I/O latency we'd like to measure. Again, sorry for operating systems 101, but I love this stuff. I like writing about it. You've got logical I/O, which is what the application is sending to the file system. That may return out of cache. It may never go to disks. And then you've got physical I/O. We're talking about storage I/O in this case. Physical I/O is actually what's sent to the storage devices, the disks. If I measure logical I/O, that's really useful because I can see all the I/O that was issued, and I typically can do it in application synchronous context, which means if the I/O was slow, the application was blocked waiting on it. If I trace down at physical I/O, by the way, the block device interface, every time you run IOStat, you're looking at the block device interface. And a lot of monitoring software out there gives you statistics based on that layer. What happens down at the block device interface can be completely asynchronous to what's happening for logical I/O. And this is such a common cause of confusion, where people are trying to understand why are my disks rattling? Why am I doing all this disk I/O load? And trying to map that to the application. And they're completely different. I/O can be inflated, deflated, unrelated. There's all sorts of different reasons why it is completely different down at the block device interface than it is up at the application. And you should start at the application level, because you can prove whether it's a problem to begin with. People worry about the disks rattling, but don't worry about that. That's just an asynchronous background job that's flushing out dirty data. It's not hurting you. I know it looks bad in IOStat, but it's not causing a synchronous problem. So for I/O flame graphs, if it's storage, I would want to go up higher, logical I/O, because I can see the latency that hurts. Just as an example, we can do this in different profilers. So for dtrace and ZFS, in this example, I go and trace some entry functions. This is at the top of the file system. I'm not within ZFS. These functions are actually the mapping between VFS and ZFS. I do a timestamp when we enter ZFS and a timestamp when we return. The delta is the time we spent. And then I can turn that into a flame graph, and I'm customizing the title. I'm actually using a little bit of awk this time because my profile data is in nanoseconds, and I'd rather it printed it in milliseconds. Just as a demonstration of why it's nice to have this at the pipe, because we can just throw things in to customize the flame graphs. And so there's the file system I/O time flame graph for gzip. Gzip waits more time in writes than it does in reads. And I can mouse over it. Did I have the example? Yes. And so this is great. I can see what it's showing me is the total time spent in that code path. So in total, in gzip flush block write buffer, in total it spent 224 milliseconds waiting on file system I/O, which we expect to be storage I/O, but it might include other things. The other really useful thing about tracing it up at the file system is that you do catch other types of I/O latency that you can't see at the block device interface. So you can't see lock contention. You can't see the earlier flame graph that I did where it was ZFS I/O throttle, which was because you're in a multi-tenant environment and we're throttling one tenant over the other. If you look at IOStat down at the disk level, you don't see that. But if you look at the top of the VFS level, it is all sources of latency. So all sources of latency, that write path is 224 milliseconds, and then the file read is 108 milliseconds. Fantastic. This one's a bit more interesting, and that's really small. So this is MySQL, something similar. And so at the big picture, I can see, I can't read it at this level, but I can see that there's a majority of time. Actually, I was profiling all applications on the system and their file system latency. And over on the right, this column is for tar. So someone was running a tar job that was archiving files. That's another application. And then this larger column is MySQL. And then I can see MySQL, there's a fork in the road where you have one big column and then a slightly smaller column. And if I investigate the fork, because like I said, forks are really interesting, I can see that the big column here was doing a MySQL join. And it's doing a row search, and it's doing going into OS file pread. And the smaller column was SQL select. And of course, the width is relative to the time you spent in this code path. And it's explaining how did I get into the file system, and why did I block, how long did I block, show me the totals. Fantastic. It's, like I said, this is not doing it at the block device interface where you're not sure whether it's an issue or not. This is the time that my application was blocked on the file system, which is typically the disks, and showing you the path that you took to get there. But I don't actually think these are cool. And the reason I don't think these are cool, I only put a couple of slides on them, is that when I'm profiling I/O stacks, there's usually only 1, 2, or 3 paths that lead to doing disk I/O, lead to doing file system I/O. And if you only have a few paths, I spot it from the profiler output straight away. So the flame graphs are nice, but a little bit overkill when I can already see it from the text output. Off-CPU is a different story. With off-CPU tracing, this is where I'm looking at the time from when I block to when an interrupt happens. And it's a generic approach for all blocking events, including I/O. So for this one, I can do I/O and I can do everything else. Every single reason you can block in an application all at once. It's an advanced performance analysis methodology that I've written up before. It's the counterpart to on-CPU profiling. And I've got so you measure time of thread spent off CPU with its stacks. Different reasons you may be off CPU. I may be waiting, sleeping on I/O, locks, timers, runnable waiting for CPU, runnable waiting for page and swap ins. The stack trace will explain which. And off-CPU profiling data durations and stacks can be rendered as off-CPU time flame graphs, which are really cool. And Yuchen Zhang created these and gave a great talk about them, based on the methodology that I had been promoting, and he's been using them to solve issues already. He had a great talk doing Nginx performance analysis. But with off-CPU latency, it is more copaths. And so very quickly, you actually need flame graphs because there's too many things to pick through. So I have examples. So you may not want to use dtrace. You may want to use something else. That's totally fine. What it's doing, just to give you a sense of how this is implemented, I'm asking my profiler to do a timestamp when the scheduler puts us off CPU for the target, say bash. And then when we go on CPU, I calculate the delta time, the time we were off CPU. And then I can sum it by whether it's a user stack backtrace or kernel stack backtrace or both. And then I can turn that into a flame graph. So here's the bash shell. And I can see most of our time was in this column, which is read command, read token, read line, read key. 12 seconds are in read key. That's keystrokes. This column over here is in waiting for child processes, wait PID. Cool. I'm tracing every single reason bash might leave the CPU. Show me why. If I want to know why it's on CPU, then I can use the CPU flame graph. But this is a generic approach to look at any type of latency. Now, of course, that's too simple. I wouldn't actually do a flame graph for that. It's only 2 columns. I would do it for more complicated things like MySQL. And so here's the off-CPU time flame graph from MySQL. And what's interesting about this one is that this MySQL that I generated it for was completely idle. This is an idle MySQL. It's not doing anything. And if I mouse over it, I can see the names. So at the very bottom, we're in thread setup. If I go up the stack, the reason we're blocked includes things like LWP park. We're waiting on a conditional variable. So we're waiting on some event. And it's the same basically for all of these. So I've got an idle MySQL. I generate a off-CPU flame graph, and it tells me I'm just blocked waiting on something else. OK, get it. That's not a surprise. What's interesting is I can look at the bottom, and I can identify all of these threads that MySQL has. So each of these columns comes from different threads that are starting from down there, or different copaths. And I decorated that flame graph with all of the names. So kind of I wasn't expecting off-CPU profiling of an idle application to be so interesting, but it was actually pretty interesting. What I've also done is, this is similar, but at the top of each stack, I draw an extra box showing the time each thread was spent off CPU. And so now you count the boxes, and you can see how many threads were in that column. So there's one thread was in that path, 2 threads were in that path, many threads were over in this large area. And the size is also relative. I'm not just putting boxes so you can see the multi-threaded code paths. Those thinner, narrow boxes are threads doing more work, so they're spending less time idle. So fantastic. Now I can see how the application is structured for multi-threaded programming. I can identify the different threads. But I still don't get super excited about off-CPU profiling. It's actually really cool. It does solve a whole bunch of issues. But the problem with it is that the CPU stacks often don't explain themselves. And we just saw that with MySQL anyway, where it's waiting on a conditional variable. OK, so what's causing the latency? Well, you can't tell. Someone else, you're waiting on a wake-up event from someone else. Just to show what a busy MySQL server looks like, now it's different. We're actually waiting on packets because we're doing networking. So that's pretty cool. This busy server also has something interesting. We have these random narrow stacks, which are occurring during work. So why would we block during my ISMB-char UTF-8? And if you see this, if you see random narrow stacks for off-CPU profiling, include the kernel stack trace, because the kernel stack trace may explain why, and it may be involuntary context switches because you're at the end of your CPU time slice. So I said that was the counterpart to on-CPU profiling, so let's do both. On-CPU profiling shows what's executing. Off-CPU profiling shows every other state. And I previously talked about this last year at LISA as a methodology, the stack profile method, where we do on-CPU profiling and off-CPU profiling so that we can identify everything. And I can put them on the same flame graph and call it a hot-cold flame graph. Great, fantastic. Except this actually doesn't work so well. Threads for an application spend a lot of time idle, waiting for work, and then a small amount of time actually doing the work. So interesting experiment, but in most cases, I think it's actually better to do on-CPU and off-CPU separately so that you get the full width and you can see what's going on. And the other problem with hot-cold flame graphs is that with off-CPU, you have the same problem. You can't tell. So here, we're waiting on conditional variables again. Curse those conditional variables. We should delete all conditional variables. Code would go so much faster if we weren't spending time in conditional variables. The problem is they don't explain why we're waiting. A conditional variable means I'm waiting on someone else. So same problem. Not as exciting as it sounded. That was the state of the art. So up until when I was proposing this presentation for LISA, that's as far as we had gone. But it was really frustrating to be so close and to think we can do on-CPU profiling, we can do off-CPU profiling, but we can't see, when we go into these conditional variables and we're waiting on someone else, we can't see their call stack. We can't see the reason that we're blocking. And that led me to doing wake-up tracing. And with wake-up tracing, you trace, because if you're blocked on someone else, guess what? The kernel knows who that someone else is, and you can trace them, and you can get information from them. And if you can associate together, you can live the dream. And you can have an on-CPU flame graph that shows all the reasons you're on CPU, an off-CPU flame graph that shows all the reasons you're off CPU, including who's waking up those conditional variables. This would be fantastic. It will solve every performance problem if you can visualize it, if it can work. And this is what I've been feverishly working on so that I can present it here. So this is all brand new stuff. Wake up latency flame graph. This shows the off-CPU time that for SSH, just as an example. And I can see, it's a bit small, but we're doing, this is the typical problem where we're in conditional variables. And looking at the off-CPU flame graph, it doesn't actually explain what's going on. At the top, I decorate it with the threads, but I also decorate it with the object that we're blocked on. Now I can do a wake-up latency flame graph, and this shows other threads that were waking up those conditional variable objects. And if I associate the two, I can see I went off CPU on this object, and then I bring up the wake-up time flame graph, I find the same object, and then I can see the reason it was woken up. There are two columns here. I know it's a bit small. There are two columns here. The one on the left is, at the bottom, it's shed, it's metal, and then it goes into kernel timers. And kernel timers, oh, and then it goes into vmstat. And so that's waking up SSH. And the reason timers and vmstat were waking up SSH is that I'd run vmstat1 in a terminal window, and it was outputting at 1 second intervals, and that was causing the wake up of SSH. And this flame graph is associated together. So SSH was waiting on this other application to emit output so that it could send it, and I'm able to associate them and understand that latency. And on the right, this is actually, this is coming out of vmstat as well, so that I can see the path that led to the wake-ups. But this still doesn't solve it, because first level of wake-ups is often not enough. We'd like to programmatically follow multiple chains of wake-ups and visualize them. And I've talked to other programmers about this, and like a fantastic developer at Valve Software who's playing with flame graphs as well for analysis, who said, yeah, this is a really hard problem. You'd be interested to see if you could visualize it. And it's like, yes, it is a hard problem. If I could visualize it, I could come up with a chain graph that showed the entire sequence that led to waking up that conditional variable that we're blocked on. And I got it to work at about 4:30 a.m. this morning. And this is the chain graph. And I'm just going to have to show it to you. I didn't even name it something good. And it's really long, but what I've done is I've preserved the notion in flame graphs where width is relative, and that shows time. It was so easy to think, well, I've got this one thread over here, which is off CPU. This other thread's doing wake-ups. Maybe I should visualize it and have like an arrow between them, or like do them all sorts of different ways I can do it, but I would have lost the ability for you to visually compare the lengths and understand what's going on. So what I've done is the bottom stack, you're going to have to play with this fig. The bottom stack shows SSHD. It's going into conditional variable because it's waiting on that CV. OK, I know that. I know SSH is waiting, but why is it waiting? Then I have this divider, and then everything above it, I do reverse stacks from the origin down. So I go backwards and say that CV was woken up by spec write, fop write, and it's coming out of vmstat. And here on the right, we've got so that CV is also woken up by IP. And this column on the right is actually showing that CV was sometimes relatively woken up by BNX, which is the network driver, because SSH is waiting on it, is woken up by a network packet. And the column on the left shows that it's sometimes woken up by a timer. That timer then goes and wakes up vmstat. That thread then goes and wakes up SSH. And so this works, and I can go all the way down to metal and show this is and just lay each piece and show this thread woke up this. So you will read this top down. This thread woke up this thread, woke up this thread. Then we woke up the CV and you run. It's all relative so that my eyeballs can make sense of it quickly. So I didn't decorate this in the slides because, like I said, I just threw this together right now. But I will post this slide deck to SlideShare, and I'll add a few decorations. So fantastic! It feels great, and I want to go use these on applications as well. So that's the end of material on flame graphs. The last thing, just a very quick tour of, I just show you a development I was working on, a very quick tour of other developments in the world of flame graphs. So node.js flame graphs, Dave Pacheco developed the dtrace USENIX provider for them, and that's great because you can see the functions in node.js and understand CPU time. So many people have told me, how did we do this before flame graphs? How do we understand our node.js performance? Flame graphs make it so much easier, and they've solved countless bugs. OS X, Mark Probst developed a way to produce flame graphs from instruments, so that's great. Ruby flame graphs, Sam Safran developed them with the Ruby mini profiler. And in fact, Ruby's call stacks are so deep, he couldn't draw the function names on them, and so he dropped them. And it's really interesting, actually, because you still preserve the value of seeing the big picture at once, and then you can go into the detail. So I think that's fantastic. Windows XPerf, Bruce Dawson developed flame graphs from XPerf data. That's showing Visual Studio CPU usage. For each of these, I show the URL, which you should absolutely read. He has a great blog where he goes into detail. WebKit Web Inspector, flame charts. So Google Chrome added, inspired by flame graphs, they added what they called flame charts to Web Inspector so that you can understand JavaScript. But they did it differently, and this is why they call it, I figure this is why they call it flame charts. They're showing the passage of time, so they're not sorted alphabetically, and so they don't benefit from the merging. And they get away with it because the V8, or what they're profiling, is generally single-threaded, and it's spending a lot of time in repetitive code. So I would love them to add if you're from Google and you're in the room and you know the team doing this, I would love them to add a toggle so that you can switch between flame charts and flame graphs, which will maximize the merging. It'll be fantastic. And they've actually innovated in other areas, so you can zoom in and do all sorts of cool things of their flame graphs, flame charts. Tim Bunce added flame graphs to the Perl main profiler. And I know him from his Twitter handle, AgentZH. I mentioned him a couple of times earlier. He's been doing lots of fantastic work with flame graphs. I've got a lot of URLs there you can check out. That's a flame graph of his day, which he used to explain, just so that people can understand this is what the flame graph visualization actually does. My day, processing emails, hacking, and so on. Color schemes, there are different color schemes that we've been experimenting with, like highlighting which functions are on CPU the most. Zoomable flame graphs, Dave Pacheco has done this, where you can click, I can click on an element, and then it will zoom in so I get more details, which is really cool. At some point, because Dave Pacheco rewrote flame graphs in node.js, I think at some point his implementation will be the de facto norm and not my Perl program. So this might be the future of flame graphs, because the zooming is fantastic the way it works. Robert Mustaki at Joyent has been experimenting with flame graph differentials because we want to run flame graphs to do non-regression testing, and using color so that you can see which code paths have expanded or shrunk. And of course, when you start thinking about non-regression testing, it's like I want flame graphs every time I change my application software. And this is Pedro talked about this very, very recently at a conference where he's working on a project for every GitHub push of your node.js code, you get a flame graph that you can then compare. So I should mention flame graphs are actually inspired by Real Neil, an ex-colleague from my time at Sun. He was inspired by Roch Bourbonnet's work, another ex-colleague of mine at Sun. He'd been doing call stack analyzer for many years, which was a time series visualization of call stacks. I've got an example of Real Neil's version there. Edward Tufte also is inspirational, and he has this notion of putting all the data at once and then navigating with it. So, and that's exactly what flame graphs are. And that's the end of the talk. So thank you very much. So whatever, I hope flame graphs are really, really useful for you, and do send me if you've done implementations, put them into new things. They are appearing in lots of different products. So questions? Yes? You can hear me. So you're using 97 hertz or 99 or 100. Why is there some heuristic for choosing that number? Yeah, I'm using 99 hertz or 997 hertz. It's because I don't want to sample in lockstep with some timed activity. And I actually put this to the test one day because people were like, is that real or is that just some myth? And so I tried and tried and tried to have a clash, sampling at 100 hertz and 1000 hertz. And yes, timers are so accurate in kernels these days, you can accidentally sample in lockstep. And the flame graph or the profile will misrepresent the target because you're always sampling when something wakes up or you're always sampling when something doesn't wake up. So it's like jitter. Actually, some other profilers automatically do a degree of jitter to solve the same problem. So you don't have to do 997 hertz. Yes?
Thanks. So thanks for the talk, very useful. Kind of a tangent. If anyone sees anyone grepping log files from cron, please tell them about maybe secpl, for instance, simple event correlator that does that so much better. I know that wasn't your talk, but I cringe when I see that. I didn't write it. I'm just a happy user. Don't grep from cron. Thank you.
Cool. Thank you. If you're grepping from cron, please look at the other technologies to do this much better. Other questions? Okay, I will get my slides onto SlideShare, and like I said, I'll get the examples figs on GitHub, all the code's on GitHub, so you can play with it, and I hope it's really useful. So thank you.